Thank you, everyone. So yeah, today we were given the task of summarizing the measurements and the prospects of high energy neutrinos. And by high energy, we mean above GeV coming from natural sources. And so Ali later will talk to you about the direction and time of these neutrinos, but in my talk, I will focus on the energy and flavor observables. And so I'll tell you a little bit about astrophysical neutrino measurements, how we can use neutrino flavor to probe new physics, and the role of tau neutrinos and atmospheric neutrinos in high energy detectors. So these are the neutrinos that you get for free. We've heard a lot today about the diffuse supernova background and supernova neutrinos, as well as solar neutrinos in the past days, but I will focus more on the 10 GeV and higher energies, mainly atmospheric, astrophysical neutrinos that are hypothesized to come from active galactic nuclei or transient events such as gamma ray bursts, and then at the highest energies, a diffuse flux of what's called GZK neutrinos that I'll talk about a little bit more. Of course, you get the neutrinos for free, but you don't catch them for free. And so we've had to do a lot to increase our active volume mass over the years. Since Hanford, notably, we've increased the active volume mass by about 10 orders of magnitude, which is a major feat. But this was realized all the way back in 1960 when we only had one neutrino experiment by Markov, who said, we proposed setting up apparatus in an underground lake or deep in the ocean in order to separate charged particles by Cherenkov radiation. And of course, at the time, this was a crazy idea, but almost 50 years later, the construction of IceCube was completed, and detectors such as Super Kamiokande also were able to do this. And so with the burst that you see here in Cherenkov radiation technology, we were able to realize this, this vision. So I'm a member of the IceCube experiment. And the IceCube experiment is a cubic kilometer of ice instrumented in the geographic South Pole. It's composed of 86 strings of digital optical modules that are each its own detector in a way. It houses its own high voltage system and data acquisition. And they are separated by 17 meters vertically and then 125 meters between each string. There's also a smaller detector that's more densely filled in the center that we'll talk about a little bit later. And so basically what we see is lines and blobs. That's most of the events that we detect in IceCube. We call the lines tracks, and those are caused by mostly muons, but the signal that we're looking for is a muon neutrino CC interaction that creates a muon. Of course, most of these events are not contained in the detector, and so the energy resolution is about a factor of 2. But we get very good angular resolution, which is about 0.3 degrees at 100 TeV. For the cascades, this could be either electron or tau neutrino CC and all flavor neutral current interactions. So these are mostly contained within the detector. So we get a pretty good angular energy resolution, about 15%. This is also at 100 TeV. But the angular resolution suffers here. We still get a pretty good angular resolution because we use the first detected light to do this sorts of measurements, and that it's a little bit asymmetric, but doesn't look like it. The last signature is a double cascade, and I will talk more about that later, but that's mainly caused by a tau neutrino charge current interaction where the tau is created and then it decays. So you see 2 of them. Okay, so we've been able to detect astrophysical neutrinos with IceCube in 2 different ways. The first is by using the Earth as an overburden. And so that's basically as much of an overburden that you can have on Earth. You just look up and you block all of the muons coming from the atmosphere, and you're left with just neutrinos that are either created in the atmosphere or coming from the galaxy or outside of the galaxy. And so if you see an upgoing muon, you're basically certain that it's caused by a muon neutrino charge current interaction. Another point here is that muons travel several kilometers in ice, and so you have an effective increase in your active volume from the muon range, and so we see more than a kilometer cubed in an IceCube from muons. And so our effective volume is increased. Of course, the energy resolution, like I said, suffers. So this is what these muons look like. This is number of events as a function of the energy proxy in 9.5 years of data. This was recently published, I think, a couple of months ago. And you can see here, most of the contribution comes from the atmospheric flux, but the atmospheric flux drops much faster than the astrophysical, and at about 200 TeV in deposited muon energy, these two lines cross, and so we are able to distinguish the astrophysical from the atmospheric component. There's also an angular dependence that I don't show here, but we use these two handles to measure that. This flux best fits a single power law with a spectral index of 2.37. As you can see, it's been slowly getting softer and softer over the years because our modeling of the atmospheric neutrinos has become much better over the last few years. Okay, the next sample is the high energy starting events. And in this sample, we use an outer layer of the detector as a veto. So now your detector is smaller, but you are able to look at the entire sky. And so we reject any signal that is deposited in the veto region, which rejects most muons. We can also reject any signal that starts inside the detector but is accompanied by a muon, which if your neutrino is created in the atmosphere, it will be accompanied by a muon. And so this gives us a very good suppression of the atmospheric background in the downgoing region. So what we want is events that start inside the detector and have no accompanying light that's coincident. And so here you can see at 100 TeV, just to use an example, this is the flux as a function of cosine zenith, and you see the suppression using the veto. The atmospheric muons, which are in orange, are suppressed, and the astrophysical flux sticks out. So this gives you a high astrophysical neutrino purity sample, but low statistics. And we have new results with 7.5 years of data, and you can see here what I showed you earlier. The astrophysical signal clearly sticks out from the suppressed background. This is what the flux looks like. There's only 102 events in 7.5 years. We only fit events above 60 TeVs to avoid the atmospheric muon background in the downgoing region. And we have recently made the data in Monte Carlo as well as the fitting code publicly available. And it's already been used by several outside groups to test exotic models with the Ascii data. And we've been told it's easy to use, so you can download it and just give it a flux that you want to test, and it will fit all the normal components for you, plus whatever you want to add to it. So have fun with that. However, we cannot, assuming standard astrophysical sources, we cannot yet find features in our fluxes, so we don't know how many components, how many populations of sources are responsible for this flux, and we need much more statistics. Another very important observable that we have is the astrophysical neutrino flavor. So what we do is we measure the flavor at Earth, but these neutrinos are oscillated from the source, and there are 3 standard scenarios, let's say, for emission from the source, and that's either dominated by neutron decay, pion production, or muon damped is what we call it, is where the muon is stopped before it can decay. But when these neutrinos oscillate over cosmological distances, they arrive with roughly 1:1:1 ratio at Earth. And then what you see here, this butterfly, is all the allowed flavor fractions that can arrive at Earth given our knowledge of the neutrino oscillations parameters today. Now, this triangle just shows you the fraction of each flavor. So this would be a corner would be, here would be 100% nu mu, 100% nu e, 100% nu tau, and then a third of each would be right in the middle. And so any deviation from standard oscillations in flavor measurements is a smoking gun for new physics. So if we measure the flavor to be in this region, you've definitely found new physics. We won't be able to tell exactly what it is, but you can test different models and so on. So this is what we have right now. This is the measurement from Ascii that I just showed you earlier. So still we suffer from statistics. We're also limited in our particle identification capability in the current configuration, but telescopes in water, as well as the next generation of IceCube, are expected to have a much better handle on this, and we are expected to basically have a sensitivity that will cover this entire region. So we'll definitely be able to tell in the next generation what is the source mechanism. We will also have input from the terrestrial experiments. So these regions will be tightened as well as we get more precise measurements of the oscillation parameters. So the very few handles that we have in IceCube for flavor, we could definitely tell when a 6.3 PeV Nui bar hits our detector, because that produces a W on shell. And this is just a single flavor at one energy that we can identify, but it's a very good one. And so here is the reconstructed energy of this event that we saw a couple of years ago, where the vertex happened just outside the detector, but it deposited around 6 PeV in energy. And this was recently published in Nature. We have reasons to believe this is a Glashow event, because we were able to see the leading muon from the hadronic shower of this event, and I can talk more about this if you're interested. We can discuss, but for now I'll move on. So another handle that we need to get our hands on is the tau neutrinos. So I showed you earlier that in a tau neutrino scenario you see a double cascade, but this is not what reality is, because this is more than 500 meters and the tau decay length is on average 50 meters per PeV, and it follows an exponential distribution. So this would be 100 PeV tau neutrino, which we expect to see basically done in 10 years of data. What we actually see is something like this. And so this is the tau candidate that we have in our analyses. It has a decay length of about 17 meters. And the reason we have good reason to believe it's actually a tau neutrino is because we see 2 deposits of light in the PMTs that were near the vertex. And so this event had 90 TeVs deposited energy, and it was identified in 3 independent analyses using different techniques to identify it. So some analyses looked at the morphology, and some looked at the DOM pulses themselves, and they all identified the same event independently. Okay, but in order to fix this, we need detectors that can detect tau neutrinos with precision. And the next generation is aiming at that. There are multiple experiments being proposed to be sensitive to tau neutrinos specifically. One of those is TAMBO. And so this is proposed to be deployed in the Colca Valley. The idea is that you use a very narrow and deep valley in Peru, and you look for tau neutrinos that interact in the mountain. Now, if you have a muon, it will go straight through, so it will not decay within this distance. But a tau is short-lived enough that it will decay in between the 2 mountains. And so if you instrument the other side, you can basically detect the tau decay shower. It improves the tau neutrino effective area by about an order of magnitude over IceCube's current performance. So we expect to see tens of events in a few years of operation, whereas in IceCube, we've seen 1 event in 10 years. Okay, so this is where we are right now. essentially, this is where Tambo will be able to fill in a gap, because the ultra-high energy experiments that I will talk about next, which are proposed radio experiments, so those look for radio emission from EeV neutrinos, and those have a threshold of about 30 PeV, because that's where the radio emission becomes detectable. Yeah, and so the ultra-high energy neutrinos are important because these are neutrinos produced, can be produced at least by interactions of the cosmic rays with the cosmic microwave background. And we've seen the break in the cosmic ray spectrum. This was proposed back in the 60s, I think, that this could be a flux that is detectable. People have been after it for quite a while. So even though the cutoff was observed, we have not seen the neutrinos yet, and so we don't quite know what is causing this cutoff. There could be other reasons for it. Okay, so this is the target of, like I said, many experiments. So people are proposing to use, like I mentioned, the atmosphere, mountains, volcanoes, or a sliver of the Earth as a target to effectively grow your sensitive region. So this is an example of such a detector that's looking for radio emission from tau neutrinos. So these tau neutrinos would skim the Earth. This would be in a mountain range in China, instrumenting about 200,000 kilometers squared with radio antennas. And so the tau would exit, and in a similar fashion, but at a much higher energy, would decay in the atmosphere and deposit radio signals. Okay, there's also Anita, which is a radio balloon that flies over Antarctica and tries to detect radio emission coming out of the ice. This is grand. Poema is a space-based telescope that's doing a similar thing, but it uses the atmosphere of the Earth as a target, and it explores even higher energies. And you can even use fluorescent light with precision optical detectors. So you can use the big volcano in Honolulu and look for fluorescent light coming out of it, which would also be signals of tau neutrinos propagating in the atmosphere. However, these detectors have limitations. So they're limited to a very small fraction of the sky. I'm showing you here that the exit probability of a tau lepton is a function of the emergence angle. So this would be the horizon. And these are different energies of the incoming neutrino. So you see it's great for 10 to the 9 or 10 to the 10 neutrinos at about 1 or 2 degrees, but then it drops very quickly after that. And then even after 4 or 5 degrees, even if you get a tau, the energy that the tau comes out is below the radio threshold. And so this is also evident in the rate expectations from the grand experiment, where you see the differential rate as a function of elevation drops sharply after a few degrees. There's also intrinsic backgrounds for tau searches. So we found recently that basically any flavor that propagates through Earth will produce tau neutrinos as a result. And so at much higher energies, these cross sections become large enough. So you have the usual Glashow resonance, but you can also produce a W from other flavors. It's suppressed at lower energies, but becomes more important. You can also have top production. So all of these channels produce tau neutrinos after the first interaction of the other flavors. And the important point here is that what you get from electron and muon neutrinos interacting in the ice or in Earth is comparable to the actual tau neutrino flux, depending on the spectral index that you start with. And so this is the one I showed you from the muons, and this is the one I showed you from Ascii. And so this is the uncertainty we have so far. But it could be comparable and has the same shape, with the exception of this knee, which is caused by the Glashow peak. And so this is problematic. We need to account for it. And it's independent of the initial flavor you start with. So if you start with 0 electron neutrinos, you still get a comparable fraction of tau neutrinos produced. Okay. This is also Well, it's good news and bad news. Good news is that the tau neutrinos you produce from these interactions are still detectable by these proposed experiments. So we will definitely get detection in these experiments, regardless of the production and oscillation physics involved. You can think of wild BSM scenarios where no tau neutrinos arrive at Earth, but in that case, you can still see them. So that's good. We need to build those experiments. But this also means that the primary and secondary fluxes are degenerate. So if you see a tau, you don't know if it came from this flux or from this one. So what we need is a complementary synergic relationship between tau-only detectors and all-flavor detectors at these energies. Okay, another effect that plays a big role here is tau neutrino regeneration. So this was proposed in the 80s and later revisited in the 90s, and it's been discussed a lot. And this is the effect basically that is caused by just the fact that taus are very short-lived and they always decay to tau neutrinos. So what happens is your tau neutrinos are never absorbed in Earth. They always make it through. They're just cascaded down in energy. And the smallness of the neutrino cross-section is such that even if you have a 1 EeV neutrino that's going through, it only interacts 3 or 4 times. And so the outgoing neutrino has PeV energies. And so these are very high energy neutrinos that we can look for. Another important thing is that the energy, critical energy where tau's decay and interaction lengths are equal is about 1 EeV. So you need to start worrying about tau energy losses in dense media before decaying. And that's why we created this new Monte Carlo simulation. It's a MC generator at high energies, accounts for all these effects, and includes tau energy losses, polarization, and all secondary productions of neutrinos. So we've used that to look at recently the ANITA anomalous events. If you haven't heard, they reported 2 events that are seemingly coming from tau decay showers, but the incoming angle was in tension with diffuse interpretations, and so the angle was about 30 degrees below the horizon. So we used this effect to say, if you have an incoming flux that's very high energy, this would be the outgoing spectrum that would be at the detector. And so you can actually use our diffuse measurement to say, what is the maximum flux that would explain the diffuse flux if it was coming from this source. And it would have to be here, whereas the flux that was needed to explain the ANITA detection was up here. So this was severely constrained by this effect. Another important point is that for GZK neutrino detection, these EeV tau neutrinos, like I said, emerge at PeV energies. So this is one such model of GZK neutrinos. And after you propagate it through Earth, this is the North Sky averaged flux that arrives at a detector. And you see it peaks between 1 and 10 PeV, basically. But it is just below the radio threshold. So while you can see the neutrinos directly here, you can see the full sky in this range. However, you have the astrophysical neutrinos as a background now. In any case, the design of future experiments should account for this. We should be able to, the more information you have, the better it is. You will pin down such a flux. And so it is important for us to detect both the secondary and the primary flux to be able to measure things such as the cross-section, for example, at these energies, which will be very informative. Okay, now I will focus a little bit on the background and tell you a little bit about what I've been ignoring this entire time, which is the atmospheric neutrinos. So the infill array in IceCube was designed to do measurements down to about 5 GeV neutrino energy. And this is a plot that was shown recently at a snowmass discussion. So you could do things like measure tau appearance with IceCube. So this is what you would expect from oscillations in neutrino variables. And then once you propagate them to the detector. This is what it looks like in true energy and angle. And then once you've smeared them out, you can see it looks something like that. However, they're still, you can still distinguish them fairly well. And this is what that would look like in number of events as a function of L over E. As you know, we have very large uncertainties on the energy and the angle, but we also have access to a lot of energies and a lot of baselines. And so this allows us to do something where you're very sensitive to the appearance of the tau. So this is where you have no oscillations. This is when you include the oscillations, and you can see we can describe the data very well with oscillations. This is what the 3-year analysis was able to do. And this is published here. And then this is an analysis being done on 8 years of data. Will be shown, I think, at Neutrino 2022. So this is already on tape, but the first analysis only used 3 years because we were still nailing down the systematics. Another thing you can do with the atmospheric neutrinos is look for EV scale steriles. And this was a recent analysis with 8 years of IceCube data, had over 300,000 muon neutrino events. And this here is the best fit point, about 4.5 EV squared and a very large mixing angle, a p-value of 8%. And in some regions of the parameter space, it is a world-leading limit, especially between here 0.1 and 1. Okay, so the next step in this will be the IceCube upgrade. This is a fully funded upgrade of the detector that will use that will just put in 7 strings within the deep core volume. The deployment's expected in the next couple of years. It'll only take 1 pole season. As you know, you can only go to pole for 2 months out of the year. And so if you missed it 1 year, for COVID, it was closed for 2 or 3 years. And so we've had to wait quite a bit, and it was delayed. But we are going very soon, but it only requires 1 season to deploy these 7 strings. We are using multiple PMT configurations in these strings and adding calibration devices. This will control basically our major systematic uncertainty, which is the ICE model. That is the hope. And the hope is that we will reduce, for example, our angular uncertainty by more than a factor of 2 at the high energies. And so as you can see here, these strings will have only 3 meter vertical spacing and different optical modules. What this will allow us to do is reduce as well the threshold for the neutrino energies we can probe. So the expectation is that we'll be sensitive down to 1 GeV. And this also from the same talk that I just took from Tom Studard at the Niels Bohr Institute, where they do this study of the IceCube upgrade and its capabilities. And as you can see, it will be very sensitive, especially in the delta M squared parameter. Okay, so I will conclude here. IceCube measured an astrophysical neutrino flux up to 10 PeV and will soon be joined by a network of telescopes. The flavor composition is a very important tool for the discovery of new physics. And in the next generation, we will have the sensitivity to do that. Precise characterization of the flux requires a new generation of experiments. Of course, better simulation of neutrino propagation physics at extreme energies provides new opportunities, as I've shown you. And we need more data, more experiments, more telescopes, and better simulations. Thank you.
So thank you very much. Do we have any questions?
Thanks, Ibrahim. Great talk. I have 2 questions. The first, when you showed the types of sources that you may have, you have the
flavor
neutron.
triangle.
you have the neutron possibility. Can
Yes.
you comment on how likely that is? Because neutrons don't usually get accelerated to such extent as.
No, but you get neutrons. I think in scenarios where you only have I forget what scenario it is, but there are scenarios where only the neutron survives and then it decays and gives you the neutrino.
Okay, and the other one is if you go to this slide where you discussed origin of tau neutrinos from other flavors.
Yes.
In matter. There. If you go back, yeah. Why is the top production all that relevant? Why are we not discussing, for example, D meson production?
Because the D mesons, they lose energy very quickly, so the top decays immediately. The D mesons will lose energy.
Oh, interesting.
Yeah, we included the D mesons, but they didn't do anything.
Thank you.
Thanks. One question on the tau detection with current IceCube. So I don't know if I'm up to date on the statistics you have. Is it possible to see like an exponential distribution that shows this kind of 50 meter per PeV decay with the data?
Oh, no, we don't have that. We don't. This is the only candidate.
Okay, so it's still just that.
Well, there are 3 candidates, but this is the only one that we have a high degree of confidence that it could be a tau neutrino.
Okay.
But yeah, there's not many you can do that with.
And okay. And the other question is on also the flavor triangle. So you show the sources with the different flavor content, and then it all goes 1 to 1 to 1.
Mm-hmm.
Is that true no matter what your starting point is? Like what kind of sensitivity is it to?
Yeah, so the idea is that anywhere you start on this triangle, you end up inside of this bow tie.
Okay, got it. Thanks.
Put your hand up pretty early.
So actually, I had a question about this failure. So back in about 2002, I think, Cecilia Leonardini and Alexei Smirnov had this paper on if we have a cosmological lepton number in the universe, you can actually get resonant transformation and changes in your flavor evolution that would be in this plot. Of course, they didn't have this plot, but has anybody thought about this since then? And I think it's also modified by the fact that we know that synchronized oscillations change the possible asymmetries coming from the early universe.
So I don't know about that particular scenario. I know that we have. I know that we've looked at several things that, like, basically any effect that will give you a flavor change can be probed with this. I know that we've done Lorentz violation analyses with this. You can do things like sterile or neutrino decay with this. So in essence, any scenario that will put you somewhere other than here can be tested with this, but I don't know if someone has looked at that particularly.
Okay, I think we had more questions.
So in your analyses of high energy neutrinos, you have these different analyses that lead to a slightly different spectral index, right?
Mm-hmm.
How is that evolving, and to what extent does that depend on your understanding of prompt atmospheric neutrinos?
So let me answer the prompt question first. So assuming our veto works, the prompt would be much lower than the astrophysical background. So this is what the prompt would look like without the veto, and this is where the prompt is when you include the veto. Of course, we still need to measure the prompt atmospheric flux, but in this sample at least, it should not be a major impact. I don't know about the muon neutrino.
That's the veto coming from ice top that sees the air shower associated with the atmospheric event?
It's the veto layer that stops any accompanying muon.
But the idea is that you see the muons that are produced together with the atmospheric neutrinos.
In the cosmic ray shower. Yeah.
And so, even after applying the veto, that difference in spectral indices is still there, right?
Oh yes, for sure. So that's that was your other question. So let me go to the backups here. So these are all of the different measurements so far. So you see these are the through-going muons, which is the 2.37, and Ascii, which is 2.9. They still are compatible with each other at 95%. But this will get tighter with more statistics and more detectors. And there is, so far we're not able to tease out any different components. So it's very likely that there are several populations and several components that are contributing to these fluxes, but we just cannot tease it out yet.
Okay, thank you.
Yeah.
Did you have a question?
So I have a question regarding the flux of new dots that are generated after the propagation of the Earth. So you saw there in this plot the sensitivity, the flux that you can explore. But I was wondering, this type of flux is based on the assumption that all those tau neutrinos must interact inside the detector.
Are you talking about this?
No, I'm talking about a few, that one. Yeah, so there you saw like the sensitivity flux you can explore. I was wondering, this estimation consider also tau neutrinos that can interact outside of the detector, because you can also produce a muon, and also, I guess you can also look for that.
So this does not have any detector effects in it. This is only flux arriving at the detector.
So it's just a comparison of the fluxes.
Yeah. So this is just saying that these two fluxes will arrive at the detector with roughly equal values.
Okay. Thank you.
Okay, so we had some great. Oh, Alex has a question.
Well, just to wrap it up, so for the atmospheric neutrinos, there is immediately a bright future, right? You have this infill, and then you're going to get a qualitative improvement.
Yes.
So what's the timeline for getting qualitatively better knowledge of the astrophysical flux? Are we have to wait for Gen 2 or what? So
for the astrophysical flux, KM3net will be turning on soon. So their proposed timeline is 2025. And they should be able to measure astrophysical neutrinos within 2 years of data taking, 2 or 3 years. Lake Baikal should be detecting astrophysical neutrinos any day now. They are already beyond 0.5 kilometer cubed. So they're still expanding. And then there's P1 coming in the 2030s, which is in the Pacific Ocean. That's also a water detector, but that's supposed to happen much faster than KM3net because the infrastructure for powering the detector already exists, because there's a big effort for marine biology research there. And so the infrastructure exists. They just need to put the modules in the water. So that should happen in the 2030s. So once all of that happens, by then Gen 2 will also hopefully be funded. And so we'll have approximately, I think, 16 or 17 kilometers cubed in total of ice. And so then the picture will become clearer. So I would say 10, 15 years, hopefully, if I'm being optimistic.
Okay, so thanks very much. Let's thank Ibrahim again.
Thank you.